Dear friends, this video is about fundamentals of robot part 2. In this we are going to discuss about specifications of robot. In that particularly axis of robot, work volume and load carrying capacity. I am Dr.R. Professor, Department of Mechanical Engineering, RVS College of Engineering, Cylindrical. Whenever you are manufacturing or whenever you are purchasing a machine, we have to specify the machine, otherwise it is called specifications of a machine. Similar way, in a robot also, there are specifications for robot. So these specifications are given below: number of robot axis, size of the work envelope, load carrying capacity, precision of movement. There is some sub specifications like spatial resolution, accuracy, repeatability, speed of motion. We'll see one by one. Number of axis. The configuration of a robot is designated by degrees of freedom or axis of motion. Each terms are replaceable. Either we can call it as degrees of freedom or axis of motion. Both are same. The number of axis determines the overall dexterity of the robot. The robot, how well it can move the components or it can reach a particular point, that depends on its skillfulness or dexterity. The dexterity is decided by the number of axis or otherwise degrees of freedom. For in a simple case, if you want to reach a particular point, at least 2 axes are required. So in a plane, if you want to reach a point, 2 axes are required. In a space, if you want to reach a point, at least 3 axes are required. So in a plane, it is 2 axes. In a space, it requires 3 axes to reach. So degrees of freedom or axis of motion is going to decide the dexterity of the robot. So in this case, you can see in a polar coordinate robot, basically it has 3 degrees of freedom. Okay, one is the vertical traverse, that is up and down motion. Up and down motion. It can move up and down. So this is vertical traverse. This is radial traverse, a linear motion. Radial traverse, extension or retraction. And then a rotational traverse. So it can rotate. So it is a rotational traverse. Okay. So it is T, R and L. So because here there are 3, one rotational axis, again another rotational axis, and again another linear axis. So it is having 3 degrees of freedom. Basically the robot up to the wrist, it is having 3 degrees of freedom. In that, again we are going to connect the wrist assembly. The wrist assembly we know very well. There are again 3 degrees of freedom: pitch, yaw and roll. Pitch is up and down movement, yaw is right and left movement, and roll about is the wrist axis. So it is having another 3 degrees of freedom. So if we are taking the entire robot, then it is having 6 degrees of freedom or 6 axis. So this robot can be called as a 6 axis robot or 6 degrees of freedom robot. The next specification is work volume. So work volume is the term refers to the space within which the robot can manipulate its wrist end. So how well in which space, the total space or the volume of the space in which the wrist end can be moved, that is what we are calling it as work volume. The volume of space within which the wrist can move, wrist can be reached, wrist can reach, that is what we are calling it as work volume. We are going to consider only up to the wrist end. We should not consider the end effector. The end effector is an addition of the basic robot and should not be counted as robot's work volume or workspace. So the workspace is up to the wrist end, not the end effector. And the work volume is decided by what type of robot it is, the robot's configuration. And next one is the size of the body, arm and the wrist component. And third one is the limits of the robot's joint movement. Because the moving element is only the joint, so the joint is going to decide the work volume. So one is what is the type of robot, the physical configuration. Second one is the size of the elements like body, arm and the wrist. And third one is the limits of robot's joint movement. All these things decide the work volume, right? So the term work volume, again, is a space within which the robot can manipulate its wrist end. So we'll see one by one. Already we discussed about these configurations in part 1 video. So we are going to see about the configuration again and how the work volume for this, what are the work volumes for these configurations. Here you can see this is a Cartesian configuration. The Cartesian configuration is denoted as L, L, L because it is having 3 linear joints L, L and L, or otherwise it is denoted as 3P. The 3P means 3 planar joints. Okay, there are 2 joints, we are calling it as planar joint and rotational joint. Because it is having 3 linear joints, it can be also denoted as 3P. Here, the arm movement of the Cartesian configuration can be described by 3 intersecting perpendicular straight lines referred to as X, Y and Z axis. So you can see from the diagram, we can call them as X, Y and Z. X, Y and the vertical direction, what we are calling it as Z. So this is X direction, this is Y direction and this is Y direction, this is going to be Z direction. So if you can see from the diagram, this work envelope formed is going to be a rectangular work envelope, or otherwise it is a rectangular prism. So it is a rectangular work envelope is going to be formed by Cartesian configuration. So the work volume or workspace of Cartesian configuration is rectangular, rectangular, or otherwise it can be called as rectangular prism. So you can see here the work volume, how it is developed. This work volume is developed. So you can see here we are having at one point to the other point it is going to move. This is actually called as this element we are considering here. So from minimum level to the maximum level, that is what we are calling it as the horizontal stroke. So it can move from here to here. This is what we are calling it as the horizontal stroke, right? So we are seeing it from this side. So it can move from here to here. This is what we are calling it as the horizontal stroke. And next one is the vertical stroke. What is the vertical stroke? This can move up and down. So this is called as the vertical stroke. This can move up and down. This is actually the vertical stroke. Vertical stroke is Z axis actually. So this is horizontal stroke. And next one is the transverse stroke. So here this column can move here to here. Here to here it can move. That is what we are calling it as the transverse stroke. So it is the plan view. It is called as the transverse stroke. So from the minimum point to the maximum point. So this is the transverse stroke. Okay. So horizontal stroke, vertical stroke and the transverse stroke. So this is going to form a rectangular prism or rectangular work envelope. Right. The next one is, what are the advantages of Cartesian coordinate robots? The Cartesian coordinate robots have following advantages. First one is because the movement is totally linear, then because of that the controls is very simpler control. It is having a very simpler control because all the movements are going to be linear movements, and because of this linear movement they are having high degree of mechanical rigidity. Because of this high degree of mechanical rigidity, their accuracy and repeatability are also high, and they can carry heavy loads, and the weightlifting capacity does not vary at different locations within the work envelope. So within the work envelope, in all the points the load carrying capacity is not going to change. The load carrying capacity is same at different locations of the robo work envelope. So that is the advantage, these three advantages, because first one is the simpler control, second one is it is having high mechanical rigidity, accuracy and repeatability, and it is having heavy load carrying capacity, and also this load carrying capacity does not change from place to place. And disadvantages, if you are taking, Cartesian robots are generally limited in their movement to a small rectangular workspace. So this is the smallest work volume from when we are comparing with the other configuration. This is the smallest work volume. So small rectangular workspace is the disadvantage of this type of robot. And the different applications of Cartesian robots includes the following. It is used in assembly, machining operations, adhesive applications, surface finishing, inspection, water jet cutting, welding, nuclear material handling, robotic X-ray and neutron radiography, automated CNC lathe loading and operation, remotely operated decontamination. All these things are applications of Cartesian coordinate robot. The next one is cylindrical configuration. So in the cylindrical configuration is denoted as TLL because one rotational joint, the twisting joint T, and two linear joints L and L. So because it is having one rotational joint, it is denoted as R, and it is having two planar joints, we are using it as 2P. So R2P, R2P. So here cylindrical configuration consists of two orthogonal slides placed at a 90-degree angle mounted on a rotary axis. So here there are two slides, this and this, which are mounted at a 90-degree angle, which are placed at 90-degree angle and mounted on a rotary axis. So here this arm moves in and out, and this column, this slide can move in the column up and down. This is a vertical column. This slide can move up and down in the vertical column, and the column rotates at the base of the robot. So it is a rotational joint T, and this is another L, and this is another L. So it forms TLL. Okay. So this work volume of cylindrical configuration, by the name itself, the work volume of cylindrical configuration is a cylinder. How we are achieving this work volume, you can see from this diagram. You can say this is actually the horizontal stroke. What is the horizontal stroke? From this minimum level to the maximum level. This is why it is actually a hollow cylinder. This is a minimum level of this slide or this arm. This arm is minimum level. This is the maximum level. So this can move in this direction. This is actually the horizontal stroke. And then the vertical stroke, here the slide can move up and down in the column. That is what we are calling it as the vertical stroke. That's having again the vertical stroke. And this can rotate. This entire column can rotate, but the column cannot rotate 360 degree. This is the maximum swing actually. This is what we are calling it as a swing. The maximum swing, almost nearly about some 270 degree centigrade. This is the maximum swing. So these three put together is going to form a cylindrical coordinate robot. It's not exactly a cylinder, three-quarter cylinder we can say. That is going to be the work volume of the cylindrical coordinate robot. So when you are comparing with the Cartesian coordinate system, we need a sophisticated control. First one is in the case of Cartesian coordinate system, the control system is very simpler control system, but the complexity of the control system is going to rise in the case of cylindrical configuration. So the cylindrical configuration requires more sophisticated control system than the Cartesian configuration. Advantages of cylindrical robot. A cylindrical configuration generally results in a large work envelope than the Cartesian configuration. So when we are comparing with the previous one, the Cartesian configuration, the work envelope or work volume is larger in the case of cylindrical robot. But there are some disadvantages are also there. So here the mechanical rigidity is reduced because the robot is having a rotary axis. It must overcome the inertia of the object when rotating. So because it is having a rotational axis, it has to overcome the inertia of the object while rotating. That will reduce the mechanical rigidity. And the repeatability and accuracy are also reduced the direction of rotary movement. So the accuracy and repeatability is low, as well as the mechanical rigidity is reduced. These two are the disadvantages of cylindrical robot. And the applications, if you are saying, they are ideally suited for pick and place operations. Cylindrical robots are ideally suited for pick and place operations. These are all the various applications like machine loading and unloading, investment casting, conveyor pallet transfers, foundry and forging applications. In all these applications we are using cylindrical robot. The third one, the polar or spherical configuration. Polar or spherical configuration. Here we are having a pivot point where which actually the robot is having its vertical movement, and the telescopic boom which extends and retracts, and at the bottom there is going to be a rotary movement around an axis perpendicular to the base. So there is a rotary base and then a vertical movement and then a reach. So again this is T joint, this is R joint, and this is L. So TRL. We are having a notation of TRL. Since we are having two rotational joints, we call it as 2RP. 2R represents the two rotational joint and L represents the planar joint. So 2RP. So there is a rotary motion at the base. This is going to be a swiveling action actually, up and down, and there is a linear movement. So the workspace created by the polar configuration robot is almost a sphere. So you can see here the work volume of a polar coordinate robot. So if you are taking this swiveling motion, that is what we are calling it as a vertical stroke, this will move like this. So that is the vertical stroke, and there is a telescopic boom which moves in and out, that is actually the horizontal stroke, and this bottom is going to swivel. So you can consider this bottom can swing, and this swinging action is going to cause this. So this boom can move in and out, that is actually horizontal stroke. This can go up and down, that is actually causing this vertical stroke, and the bottom base which is going to swing, and this is going to cause a swinging motion, or this is causing this external periphery. Okay, this external periphery. Okay, so because of this we are having a spherical work volume. It is not completely spherical. It is a part of sphere actually. It is going to have. So what is this inner radius and outer radius? This inner radius of the sphere, that represents the minimum distance of the boom. Okay, that is where actually the boom is intruded. So that is this radius, and it is in the extension position. So that is in the retraction position, and that is in the extension position, completely extended position. That is the outer radius. So inner radius is retraction position, and outer radius is the extended position. And this swing is going to cause actually a sphere. So this is the work volume of a polar coordinate robot or a spherical coordinate robot. So the advantages, and when you are taking the control system is more sophisticated or more complicated than the previous two, Cartesian or cylindrical configuration. So the control system is going to be complicated than the Cartesian or cylindrical configuration. We are taking the advantages because it provides a larger work envelope than Cartesian or cylindrical configuration. So the spherical work volume or polar coordinate robot, the work volume of polar coordinate robot is larger than the Cartesian or cylindrical configuration. And the design is simple and provides good weightlifting capabilities. And the disadvantages, similar to the previous case, cylindrical coordinate robot, its mechanical rigidity is reduced, and the same problems with inertia as well as the accuracy and repeatability of the robot is also reduced. So because of the reduction in mechanical rigidity, the accuracy is also getting reduced because the same problem, the inertia. Okay. So next one is the applications. So here the vertical movement is limited. The configuration is suited for applications where a small amount of vertical movement is adequate, such as loading and unloading. So these applications like die casting, injection molding, forging, machine tool loading, heat treating, glass handling, parts cleaning, dip coating, press loading, material transfer, stacking and unstacking, all these cases is mainly used for loading and unloading applications, spherical coordinate robot. The last one is articulated or jointed arm configuration. Can be called as articulated robot or revolute robot or jointed arm configuration. So here we are having it is almost similar like a human arm. So it is called as anthropomorphic anthropomorphic robot also. So here the revolute configuration or jointed arm configuration is the most common type of robot. Here it is having two arms. One is called as the upper arm and another one is the lower arm. So otherwise it is called as the forearm and the upper arm. Here there are two joints. You can see here this is actually elbow. Elbow connects the upper arm and the forearm, and the upper arm is connected to the shoulder, and then the joint called the strip represents the waist. So this is going to rotate completely. So this is actually called as the waist. Okay. So this all the joints are going to be rotational joints. So this is a T joint, twist or rotate, rotational joint. This is again a rotational joint, and this is again a rotational joint. So the waist, shoulder and elbow all are going to be the rotational joint. So it is denoted as TRR or 3R. So this is again a wrist assembly. You will not bother about the wrist assembly. So TRR, all the joints are rotational joints. Because of that it is called as 3R. So if you take the work volume again, this is the horizontal reach and this is going to be the vertical reach, right? Horizontal reach and vertical reach, and the swing. The waist is going to swing, so the swinging action. This is horizontal and vertical stroke. Okay, so this is going to form almost a sphere, but the inner sphere is not going to be the same. It depends upon the positions. Actually it is going to vary, the shape is going to vary, but the outer is going to be more or less the spherical shape. So this is the work volume of a jointed arm robot. So the advantages of articulated robot: it is a more versatile configuration than the previous three, and it provides a large work envelope than the Cartesian, cylindrical or spherical configuration. The work envelope is larger, or I can say the largest work envelope the articulated configuration robot can provide. And next one is it is a more flexible reach than the other configuration, making it ideally suited to welding and spray painting operations. So the disadvantages: the controller. We are talking about the controller. The Cartesian is very simple one. then the sophistication increases in cylindrical, further sophistication increases in polar coordinate system. So the most sophisticated controller is required for articulated configuration robo, and programming is more complex. And one more thing is different work locations or different locations in the work envelope can affect the accuracy, load carrying capacity as well as repeatability. So all these three, accuracy, repeatability and load carrying capacity, all these three are getting affected, or it is depending upon the locations they are going to vary. Simply we know for a human arm at an extended position it is having lesser rigidity. You can't hold the weight at the extended position, but when you are folding your elbow, you can handle more weight than the extended position. So similar way, this articulated configuration robo at the extended position, it can't carry more load, and if it carries more load, it will cause actually the vibration, or the dynamics is going to change, and because of that the accuracy and repeatability gets decreased. That's what told in this. So the configuration also becomes less stable as the arm approaches its maximum reach. So the typical applications are automatic assembly, parts and material handling, multiple point light machinery operation, in-process inspection, palletizing, machine loading and unloading, machine vision, material cutting, material removal, thermal coating, paint and adhesive applications, welding and die casting. So the load carrying capacity, what is actually load carrying capacity? It is the maximum weight that the robot can carry when the robot's arm is in its weakest position. That is, the arm is at maximum extension. So load carrying capacity we have to consider when the robot's arm is in weakest position. Where the robot's arm is in weakest position? When the arm is at maximum extension. The arm is at maximum extension. What is its load carrying capacity? That is the load carrying capacity of the robot. So here the size, configuration, construction and drive system determine the load carrying capacity of the robot. All these things are going to determine the load carrying capacity of the robot. When you are considering the rated load carrying capacity, we have to consider total weight of the workpiece plus weight of the end effector. We have to consider the weight of the end effector also. So if you the load carrying capacity, the total weight is 6 kg and weight of the end effector is 1 kg, then total load carrying capacity, rated load carrying capacity is 7 kg. So we have to consider the weight of the end effector also in the load carrying capacity. If you are subtracting the weight of the end effector, then the total load it can lift is going to reduce. Though the rated load carrying capacity is 7 and weight of end effector is 1 kg, what is the weight it can lift? It can lift only up to 6 kgs. So this is what actually the load carrying capacity. So in this video we discussed about the axis, the various work volume and the load carrying capacity. These three are the specifications of a robot. Further specifications we will see it in the next video. Thank you.